the video for week 2 worksheet. So I'm going to try to do this quickly because it's Wednesday and I have to teach discussion in a second. So I'm going to quickly draw this mechanism. Here you're going to have a resonance structure. Right, this one's going to go to add the bromine onto this position. B is going to come from and the bromide onto that, right? Draw an energy diagram. Let's call this reactant. That's going to be A and B, and then this is going to be intermediate I. I'm going to box around so it's like obviously something different. This is energy, reactant coordinate. So the standard way that we did it, at least in Orbital 1, would be you get I. Remember, both resonance structures are I. And then you would get, I guess this would be A is thermodynamic, B is kinetic. You would get that, where B, this is going to be transition state B, double dagger. This is transition state A, double dagger, right? Which products are lower in energy? That's going to be A, because it's 8 rule, is more substituted. B's kinetic product, because it's the 1-2 product. 1-2 product is always the kinetic product. Thermodynamic product is going to be A. Which product is the major product? This is in cold temperature, minus 78 degrees Celsius. So if it's minus 78, that means that you're going to favor kinetic. So this is going to be B. Temperatures increase to 190, you're going to get the thermodynamic product. Why is the kinetic product the kinetic product? This is entropy. Entropy is what's driving it to be the kinetic product, right? And just in case you forget, remember it's like, as this comes here and grabs that hydrogen, you're going to get this, where this bromide's already really close. So entropy-wise, it's going to want to bond to the 1-2 position over the 1-4. Okay. Which alkene is the most stable? Is going to be the one that's fully conjugated. If you have sp3 hybridized, it breaks the conjugation. sp3 hybridized carbons. Draw the products. I'm going to just do this quick. Remember, you always are going to have this cyclohexene ring thing. And then for this one, don't seem to really be doing the stereochemistry, but this is the odd rule, which I taught, which is that the outside groups go down or they're dashed. So just because I'm in a hurry, I gotta do this now. Okay, we got these by the odd rule. These methyl groups will be wedged, and these will be like this. Remember, to do this, you always need to set up your diene to be like this and your dienophile to be like that. Otherwise, these odd rules and the endo rules of the CNs being dashed and whatnot, they don't work out if you don't do that. So this is like the major product. The minor product would be this. And the reason why this one forms is because of hyperconjugation, right, in the transition state. I'll show it with the next one. So with this one, right, the way you're used to drawing it would be this, right? This way. There's another way you can draw this, where you draw it like this, right? And you have your CNs this way. And what happens is, in the transition state, when you have these p orbitals, and you have the dienophile here coming up, these CN p orbitals help stabilize the transition state, right? And so that's why they go dashed like that. All right, for this one, I'll keep drawing them the way that you all are used to, because I don't think it's 100% necessary for you to be able to draw it in this type of chair formation. I don't think you have to put these dashes in. I just do. So, yeah, that's the way I was taught to do it. But Dr. Davis doesn't seem to be putting those in, so I don't think that's like a huge thing. So how many products, regio and stereo? So the way I look at it is this could react this way, or you could flip it. This one could react that way, or you could flip this. Okay, as far as electron donating, electron withdrawing, and partial positive, partial negative charges, I don't think you're really going to get much by hyperconjugation donating to get that much of a partial negative charge on the diene. So even though these are electron donating groups, I wouldn't see this as like really dictating it that you're going to get like one really major product. So I would see it as you get, you know, 2 options here times 2 over here, where it's going to be 4 products. And that would be the 2 reacted this way. Then if you flip this molecule, so the CN's on top, you get a second one. If you react it with the CN on the bottom and you flip the diene, then you get another product. And then if you flip both of them, you'll get a 4th product. And I think we'll see that. All right, this one has a degree of symmetry in it. So the diene is going to be the same whether you flip it or not. This one's going to have either like this or the other way. So this one can only have 2 products. And I'll draw these. I don't want to draw the 4 of them because that'd be kind of tedious. Like that. That's what the 2 products look like. All right, this one's symmetrical. There's going to be 1 major product on this, right? But there will be also minor ones, so we'll just say 2. But there will be 1 major one, right? These are cis. All right, this one's going to rotate, and you're going to end up with, this is a cis alkene, so it's going to be Cl. This is also cis alkene, so it's also going to be Cl. So this is going to have like 1 major product, and it's symmetrical, so we'll just say 1. The other one where you don't get the stabilization from these pi bonds is going to be so minor that I don't think that's worth saying, even mentioning. This is going to be 0. This is locked in the S-trans configuration, so there's no Diels Alder reaction. All right, that's all the questions associated with the Diels Alder reaction. We got these 2, draw all reasonable products. And the only other one, just because you could flip this like a pancake, right, is this. So you could draw other ones, but they will be a rotation of one of these. Which one's the major product? It's going to be this one. Sorry, I'm supposed to box it. I'll show the mechanistic arrows, so that's going to be like this. OME is a donating group. Aldehydes are withdrawing groups. Methoxy groups where dienes were replaced with methyl groups, right? Would the reaction rate be faster, slower? It would be slower because methyls are not as good of a donating group as methoxy groups. And remember, you want donating groups on the diene. Just trying to keep 5 minutes till discussion. So that means you would need more heat. Aldehydes were replaced with methyl groups. It would go slower and you would need more heat. So then let me just draw this reaction coordinate diagram, and I think that's the last problem. That is the last problem. So, energy. So, let's just pretend like the intermediates are all the same. This would be, and then it goes down to energy. So let's just say this is A, B, C, right? So say this is A. That means for B, it's going to be higher in energy. And again, we're just pretending like they're all going to be the same energy. They probably won't be. And C is going to be here. The reason why B is lower in energy than C is because you're still having a donating group on the diene and a withdrawing group on the dienophile, versus in C, you're going to have donating groups on both. So C is going to be slower. So these are the transition states. All right, that's it for this. And I have to go run and teach discussion. So I'll take the video for this week's worksheet after discussion today. Thank you.